This video is brought to you by mywayteaching.com.
The anomalous behavior of water has some environmental effects. What are those environmental effects? Let's see. Bodies of water, such as lakes and ponds, freeze at the top first, isn't it? As lake, it cools towards 4 degrees Celsius. Water near the surface loses energy to the atmosphere and it becomes denser and it sinks. The warmer or the less dense water near the bottom, it rises. However, once the colder water on the top reaches the temperature which is below 4 degrees Celsius, it becomes less dense and it remains at the surface where it freezes. If water did not have this property, lakes and ponds would freeze from the bottom up, which would destroy much of their animal and even plant life. So this property is helping those animals to survive because water it freezes in the top first, not at the bottom. And even in other case like gases at ordinary temperature expand more than solids and liquids. Gases at ordinary temperature, if you consider, it will expand more than solids and liquids. For liquids, the coefficient of volume expansion is relatively independent of the temperature. However, for gases, it is dependent on the temperature. For an ideal gas, the coefficient of volume expansion at constant pressure can be found from the ideal gas equation that we already studied. That is given by PV is equal to mu RT, isn't it? At constant pressure, we can write it as P delta V is equal to mu R delta T. So, in other words, we can write it as delta V by V is equal to delta T by T. That is alpha V is equal to 1 by T for ideal gas. If you consider at 0 degrees Celsius, the coefficient of volume, the value is given by 3.7 into 10 raised to minus 3 per Kelvin, which is much larger than that for solids and liquids. So here this equation what we derived alpha v is equal to 1 by T. It shows the temperature dependence of alpha v. It decreases with increase in temperature because they are inversely related, right? If temperature increases, alpha V decreases. If temperature decreases, then alpha V increases. For a gas at room temperature and constant pressure, the value of alpha V is about 3300 into 10 raised to minus 6 per Kelvin. As much as order of magnitude, which is larger than the coefficient of volume expansion of typical liquids. Okay, there is a simple relation between the coefficient of volume expansion alpha v and coefficient of linear expansion that we will denote it using alpha L. You just imagine a cube of length L that expands equally in all the directions when its temperature increases by delta T. Okay, what you just assume in your mind. Then we can write that uh, delta L increase in length is equal to alpha L L into delta T. So, increase in volume is given by 3L square delta L. So, in equation, the terms delta L square and delta L cube have been neglected since delta L is small compared to L. So on this modification, we can get delta V is equal to 3V delta L by L, which is equal to 3V alpha L delta T, which gives alpha V is equal to 3 times alpha L, the relation between volume coefficient as well as coefficient of linear expansion and coefficient of volume expansion. What happens by preventing thermal expansion of a rod by fixing its very tightly? Clearly, the rod acquires a compressive strain due to that external forces provided by the rigid support at the ends, and the corresponding stress which is set up in the rod, we call it as thermal stress if you fix the two ends of the rod. We call that kind of stress as thermal stress. Okay. For example, you just consider a steel rail of length 5 meter and area of cross section 40 centimeters square that is prevented from expanding. Okay, just consider a steel rail of length 5 meter, area of cross section 40 centimeters square, and that is prevented from expanding while the temperature rises by 10 degrees Celsius. Okay. The coefficient of linear expansion of steel, we know the value, that is given by 1.2 into 10 raised to minus 5 per Kelvin. So thus the compressive strain is given by delta L by L, that is alpha L of steel into delta T. So which is given by 1.2 into 10 raised to minus 5, and delta T is 10, that is 1.2 into 10 raised to minus 4, and Young's modulus of the steel is given by, okay, Young's modulus of steel is given by Y of steel, which is equal to 2 into 10 raised to 11 Newton per meter square. Young's modulus of steel. So the thermal stress which is developed, that is given by delta F by A, that is Y steel, that is Young's modulus, by delta L by L, which is 2.4 into 10 raised to 7 Newton per meter square, which corresponds to an external force of delta F is equal to A into Y steel, delta L by L. So that is approximately equal to 2.4 into 10 raised to 7 into 40 into 10 raised to minus 4, that is equal to 10 raised to 5 Newton. Okay. If two such steel rails fixed at their outer ends are in contact at their inner ends, a force of this magnitude can easily bend that rail. So now let us see a simple problem. Show that the coefficient of area expansions, that is delta A by delta T of a rectangular sheet of the solid is twice its linear expansivity alpha L. Okay, you just consider this rectangular sheet of the solid material of length alpha, of length A and breadth B. When the temperature increases by delta T, then area increases by, then the length A, it increases by delta A, and this breadth increases by delta B, isn't it? So that increase in length delta A is given by alpha L A into delta T, and the increase in the breadth is given by alpha L B into delta T. Then we can write the increase in area as A1. This is delta A1, delta A2, and delta A3. Isn't it? You can see that from that figure. Delta A1 plus delta A2 plus delta A3. So we can write delta A as A into delta B plus B into delta A, that is delta A2, and delta A3 is delta A into delta B. A alpha 1 B into delta T, that is if you write delta B, the value of delta B from this equation, and even the value of delta A, plus B alpha L A into delta T, and if you substitute delta A and delta B, the value we get alpha L whole square AB delta T square. Okay, that is alpha L AB delta T multiplied with 2 plus alpha L delta T. Okay, that is given by alpha L A into delta T 2 plus alpha L delta T. Since we know the value of alpha L, it is given by 10 raised to minus 5 per Kelvin. From the table, the product of alpha L and delta T for fractional temperature is small in comparison with 2. So that can be neglected. So we can write delta A by A 1 by delta T is equal to 2 into alpha L. Hence proved.